I am JB Dr. Srivastava. Today I will discuss some theorems of real analysis on the topic supremum and infimum. First, we will see the maximum element. If S is a non-empty subset of R contains the largest or greatest element M, that is X is the cycle M for all X belongs to S, then M is called the greatest element of S, and it is written as X of S is M. Greatest element of a set, if it exists, then it is unique. Least element means smallest element of the set. If a non-empty subset S of R contains a smallest element M, that is X is greater than M for all X equals to S, then M is called minimum or least element of S, and we can denote it as minimum S is equal to small m. Minimum element of the set, if it exists, is also unique. Now the supremum. Let S is a non-empty subset of R. A real number alpha is called the least upper bound of S. If first number alpha is the upper bound of the set S. Second, if alpha dash is any other bound of the set, then alpha is less than equal to alpha S. In other words, the smallest of the upper bound of the set is called the least upper bound or supremum of the set. There are the remarks: supremum of the set may or may not be in the set. There are the some examples. Now the next definition, infimum. Let S is a set not which is non-empty of R, a real number. Beta is called the greatest lower bound of S if beta is the lower bound of S. Second, if beta dash is any other lower bound of S, then beta is greater than beta dash. Remark: infimum of the set may or may not belong to the set. There are some examples. Now we see some theorems on supremum and infimum. Theorem: if supremum of a non-empty subset S of R exists, then it is unique. Let S is the non-empty subset of R, and alpha is the least upper bound of S is subset of R. So by definition, these of supremum alpha and alpha dash be the upper bound of the set R. If alpha is the supremum, then alpha dash will be other upper bound, then alpha is less or equal to alpha dash. This is equation A. And if alpha dash is the supremum, then alpha is the other upper bound of S, then we can write alpha dash is less or equal to alpha. This is equation B. Thus from equation A and B, we conclude that alpha is equal to alpha dash. So the supremum of the non-empty subset S of R, if it exists, it can be unique. Now the next definition, theorem: the greatest member of the set, if it exists, must be the supremum of the set. The greatest member of the set, if it exists, must be the supremum of the set. Let S is the subset of R and alpha is the greatest member of S. Then we can write X is less or equal to alpha for all X belongs to S. If alpha is the maximum element of S, then alpha must be the upper bound of S. Let alpha dash is any other upper bound of S, then X is less or equal to alpha dash for all X belongs to S. In particular case, alpha is less or equal to alpha S, since alpha belongs to S. Thus, alpha is the least upper bound of the set. Hence, the greatest member of the set, if it exists, must be the supremum of the set. Now the next theorem: if S is a non-empty subset of R which is bounded above, then a real number alpha is supremum of S if and only if X is less or equal to alpha for R X belongs to X. Second, for each epsilon is greater than 0, there exists at least one x belongs to S such that x is greater than alpha minus epsilon. Given alpha is the supremum of S is subset of R, so alpha be the supreme upper bound of S. Then by definition of upper bound, x is less or equal to alpha for all integers to S. So first condition is correct. Now further, if epsilon is greater than 0, then alpha minus epsilon is less than alpha. Therefore, alpha minus epsilon is not the supremum or upper bound of S. Then there exists at least one element x is greater than alpha minus epsilon for some x belongs to S. So second condition is also correct. Now conversely, if alpha is any real number which satisfied by the given condition first and second, then our aim is to show that alpha is supreme. From first, x is less or equal to alpha or all x belongs to S. That implies alpha is upper bound of S. Let alpha dash is any other real number of S such that alpha is greater than alpha dash, then alpha minus alpha dash is greater than 0. Now taking epsilon is equal to alpha minus alpha dash. By condition second, x is greater than alpha minus epsilon, that implies x is greater than alpha minus dash. That implies x is greater than alpha dash. That implies x is greater than alpha dash. That is, there exists at least one element x belongs to S such that alpha dash cannot be upper bound of the set S. Thus, every real number less than alpha is not an upper bound of the set S. Hence, alpha is the supremum. Now, the next theorem: if supremum of subset S of R exists, then it is unique. Let beta and beta dash are two infimum of the set S, or we can say that beta and beta dash are just lower bound of S. So, by the definition of infimum, beta and beta dash are two lower bound of the set S, which is subset of R. If beta is the infimum, then beta dash will be other lower bound. Then beta is greater than beta dash. This is first. If beta dash is infimum, then beta will be other lower bound, then beta dash is greater than beta. So from equation first and second, we conclude that beta is equal to beta dash. Since the value of beta and beta dash is same, so beta and beta dash are not distinct or different. They are same real number. Thus, if infimum of the subset S of R exists, then it is unique. Now the next theorem prove that the smallest member of the set exists must be the infimum of the set S. Let a non-empty subset S of R. Let beta is the smallest element of the set S. So by the definition of the smallest member, beta is less or equal to x for all x belongs to S. This is equation first. Equation first satisfied by the definition of lower bound. So, beta is also the lower bound of the set S. Now, we have to prove that beta is the greatest number of the lower bound of set S. Let beta dash be another lower bound of the set S subset of R. So, by a definition of lower bound, beta dash is less or equal to x for all x equal to S. This is equation second. From equation first and second, conclude that beta is not equal to beta dash. Beta and beta dash both are the lower bound of set S. It is given that beta is the smallest member of the set S, so it belongs to the set S. Beta belongs to S, but beta dash does not belong to the set S. If it is belongs to S, then beta dash is not the lower bound of S because there exists a element x belongs to S such that x is less than equal to beta dash. So it exists out of the set, that is beta dash does not belong to S. Beta dash is less than equal to beta. Since beta is the greatest of all lower bound of the set, thus beta is the infimum, means greatest lower bound of the set. Now here is the theorem. Now the next theorem. Between two distinct real numbers, there are infinitely many rational numbers. Let x and y are two real numbers such that y is greater than x and y minus x is greater than 0. Now let y minus x and 1 are the distinct real number. Then by the argument property, we can write n of y minus x is greater than 1. This is n y minus x is greater than 1. This is n y is greater than 1 plus nx. 1 plus nx is less than ny. Since 1 plus nx is a real number, then there exists at least one natural number, say m, such that m is less or equal to 1 plus nx is less than n plus 1. From it, m is less or equal to 1 plus nx is less than ny is equal to second. Again from E, 1 plus nx is less than n plus 1. This is nx is less than m. Then from C, nx is less than m is less than nx is less than ny. Again, nx is less than m is less than ny. If this it can be written as x is less than my, n is less than y. Thus, between two real numbers x and y, there exists a rational number m by n, that is r1. We can write x is less than r1 is less than y. Now x and r1 are two real numbers, and repeating the above process, we obtain a rational number r2 such that x is less than r2 is less than r1 is less than y. Now, continuing this process, we can see that there are infinitely many rational numbers between x and